environment from geophysical application. This course is coordinated by Bapak Dr. Wahyudi Parnadi, lecturer from Geophysical Engineering, Bandung Institute of Technology. I am Harmita Lestari from Geophysical Engineering, Bandung Institute of Technology, as a moderator for this session. And today is the day 6, and we are going to the session 2 with Bapak Profesor Wayan Sengara. How are you today, Bapak Profesor Wayan Sengara? Bapak Profesor Wayan Sengara is lecturer from Bandung Institute of Technology, and our topic for this session is slope stability analysis, theory and its application in geotechnical engineering. So we are very happy to have you, Bapak Profesor Wayan Sengara, to share your knowledge and experiences to all the students. And first, let me to share my screen. I will read the CV from Bapak Profesor Wayan Sengara. So, Bapak Profesor Wayan Sengara is lecturer from Bandung Institute of Technology, and you can see here is the email address from Bapak Profesor Wayan Sengara, and his education and qualifications, bachelor degree from Bandung Institute of Technology, and master degree from University of Wisconsin-Madison USA, and doctoral from University of Wisconsin-Madison USA. And the position is a professor, and the previous publication over 61 publication on Google Scholar and over 417 citations. The skills and expertise: geotechnical engineering, earthquake engineering, and soil structure interactions. And the latest projects, Board of Experts worked on underground powerhouse design, review #1 PLTA Peusangan, and new 2019 rigs targeted ground motion for spectral design criteria in Indonesia, seismic building code, and development of design acceleration response spectrum for building based on new Indonesia seismic hazard maps 2017. So now we are going to the I'm sorry, I think my mic is already. We will wait until the azan again. I'm sorry. Pak Wahyudi, do you hear my voice when I read the CV?
Yes.
Okay, thank you. So, Bapak Profesor Wayan Sengara, you have about 1 hour and 30 minutes to deliver your presentations and 30 minutes to question and answer session. So, ladies and gentlemen, let's welcome Bapak Profesor Wayan Sengara to share his presentation. Bapak Profesor Wayan Sengara, time is yours.
Okay, thank you very much, Harmita. And I would like to appreciate Dr. Widyatmoko as the coordinator for this international video course. This is a series of courses that's offered by the Faculty of Mineral Science to many undergraduate students, I think mostly undergraduate students. So let me share my screen. Harmita, could you open the share screen for me?
Yes, sure. You can share your screen and the host will accept.
Looks like that the host is still disabled for me.
Can you try again, Bapak Professor?
No, I still cannot.
Still can. I think the host is Pak Wahyudi. So Pak Wahyudi can accept your screen to share. Pak Wahyudi, can you hear me?
Yes, I change host now to you.
Okay, thank you. Bapak Profesor Wayan Sengara, you can try again, please.
Not yet.
Okay, wait.
Do I need to just a second?
How about now? Still can.
Okay. Yeah, I think I can make it now.
Okay, thank you.
So can you
I'm sorry, I
see
think the
my
connection.
no?
Yes, clearly. You can continue.
Can you see my screen?
Yes.
Okay. Let me start my lecture tonight. My lecture is about slope stability analysis theory and its application in geotechnical engineering. So I would like to present this lecture. First one is the introduction on slope stability in general, because I know the participant for this course is probably from many departments, from civil engineering department, from geophysics, and other related field. So I would like to introduce the nature of the slope stability. So that we have the same understanding of what is the slope stability. And the second one is the factors contributing to slope failures. And the third one is factor of safety. So usually we quantify the stability of slope by what we call factor of safety. And also we need to understand what is the failure mechanism, what is the failure criteria for soil layers. So this will be explained and elaborated through what we call Mohr-Coulomb failure criteria. And in the fourth section will be the analysis of the slope stability itself. I would like to explain two types of slopes here. One is the infinite slope, and the second one is the finite slope. And last one is some cases in practical application of slope stability analysis. Let me start with the introduction of slope. Well, the slopes are typically categorized in two types. The first one is natural slope. As you can see in many areas, the slope is formed by the natural state and artificial made slope. So this is a man-made slope. Usually we are in civil engineering design and construct many man-made slopes. In other engineering profession, like in mining, for example, there is an open pit mining. There is maybe tailing dams, many other facilities or infrastructure are actually man-made slope. So that we need to design that slope. Natural slope are formed due to physical processes that include plate tectonics and weathering or erosion of rock masses that result in material deposition. Whereas artificial slopes are established to facilitate infrastructure project, etc. For example, embankment of dams, road cutting, and so forth. Let us see the origin of soils and rocks, where we have many slope problems when we whether we have a natural slope or man-made slope, where we have either soil layers or rock layers, which is actually soil and rock is abundant in this nature. So this is just illustration on how the soils and rock form that could be either each of this formation. The first one here, let's see. Okay, just a second. This is a sedimentary rock. Sedimentary rock. This is called a rock cycle. When we have a sedimentary, or maybe we can start with the let's say igneous rock. So this is a very hard rock that we found in it could be eroded or weathered, become a sediment. So there is another form of a rock that called rock sediment, and this sediment also could compact or change in action, cementation, and sediment to become sedimentary rock. And then from sedimentary rock, because of metamorphism, then this rock, sedimentary rock, then become a metamorphic rock, and through melting, through magma from the volcano, for example, and then return to become an igneous rock. So this is actually for the nature of the rock cycle, where the soil is actually the weathering of this rock. So soils and rock is actually common in nature. Soil and rock has a very similar formation, except that soil is much softer compared to rock. So in nature, we have a slope problem, either in the rock formation or in the soil formation, depending on the slope of the whether it is stable or not. A slope movement, also referred as a landslide. You have heard of a word landslides, and many landslides occur across the world, can lead to severe issues, including infrastructure damage and or casualties. This slope stability depends on the capability of the soil mass to withstand its gravitational forces, and the additional load acting on the slope, as well as potential dynamic loads such as earthquake. Well, a common misconception is that landslides steep and remote slope, and it doesn't, or they do not actually impact human infrastructure. However, statistics show that most of the world's region are impacted by at least some type of landslide phenomena that can be triggered by several factors, including erosion, precipitation. This is from rainfall due to earthquake that could trigger dynamic loads, and also load because of our construction. So that is some general introduction of the slope. Here we have some example of slope failure. This is massive landslides at the Kennecott, Utah copper Brigham Canyon mine production at the second largest copper producer in the United States. The landslide occurred in 2013, not long ago. So we can see how this massive failure occurred in the open pit mining, while this could be due to many factors, including the rainfall, including the well, because this the safety factor of the slope is with very low margin of safety, so that with the small trigger, maybe due to rainfall or dynamic loading, it could fail. I'm not sure how this slope failed, but the fact is the original slope is stable, like in this part of the slope, but in some section is very critical, and then finally it failed. Well, that is in the mining activity, and this one is a dam. This is, of course, this is man-made embankment or man-made slope. This dam is in Australia because of the seepage, because of the flow of the water of the reservoir. This slope, this dam failed. This is a very catastrophic failure. And this one also, this is natural slope. This one is man-made slope. If we come back here, this is also we call man-made slope. This one is natural slope. That impact the house in this area severely below. This is in El Salvador, 2001. Well, you can maybe guess where is this? This is in close to Bandung area here. Last year in 2020, this is a toll road, Jakarta-Bandung toll road, and we can see some of the failure occur because of the in one part of the slope, in one part of this toll road. And then because of some seepage, groundwater flow within this, the right part of the toll road, and then the right part of the road and fail. And you can see here we have a very large mass of soil going on the lowland of this area. There was actually some concern on the what's going to happen with this toll road. Well, there is some reinforcement, some soil improvement, slope stability construction conducted at the time. Okay, many slope the nature of the slope failure include fall, topple, slide, spread, flow. Many types of slope failure could occur in some basically in the natural slope. On the very top here, the very top left, this is a type of what we call fall. Maybe a rock fall, if there is a rock within the slope, and if we have a fractured rock like this one, it could be slope failure by toppling, just the upper part of this it to many factors, whether there is a rainfall, earthquake, or many other cause. Well, this one, this is sliding, mostly occur in soil, what we call soil with no fracture, but mostly homogeneous with lower strength of the subsurface. We have, we call it sliding. And here we have lateral spreading. Usually this slope failure occur because we have some layer of very soft in strength. The top one might be a higher strength, but after fail, there is a fracture of the soil material because of the heat. And this one is the slope failure by flowing. It's just like a fluid. Many failure occur in type soil because of the combination with the precipitation and then
I'm sorry, I think there is a problem with the connection. We will wait Bapak Profesor Wayan Sengara to join again. So to all participants, now the topic is...
sorry.
Okay, no problem. I think your connection is a problem.
I think there's some bad connection.
Yes.
I think a problem in
Yes.
my connection.
You can share your screen again. No problem.
Okay.
I think your microphone is off. Bapak Profesor Wayan Sengara, you can continue your presentation. Oh. Bapak Profesor Wayan Sengara, you can turn off your camera to make better connection during your presentation. So to all participants, now the topic is slope stability analysis, theory and its application in geotechnical engineering. Okay, I can see your screen. You can continue. I'm sorry, but I think your mic is still off. I'm sorry, but your mic is still off. Your microphone. Professor Ryan Sengara, can you hear me? Your microphone is still off. I'm sorry. We cannot hear your voice.
Can you hear me now? Hello?
Yes, clearly.
Okay.
I'm sorry,
Okay, sorry.
you can turn off your camera during your presentation to make a better connection.
Yeah, sorry about the bad connection. Okay, let us continue with the objective.
Yes, of course.
Yeah, in most application, the primary purpose of slope stability analysis is to contribute to the safe and economic design of excavation, embankments, earth dams, landfill, and spoil heaps. So furthermore, the aim of slope stability analysis are to understand the development and form of natural slopes and the processes responsible for different natural features. To assess the stability of the slope under short-term, usually for man-made slope, we call it during construction, and also for long-term construction. Number 3 is to assess the possibility of landslides involving natural or existing engineered slopes. To analyze landslide and to understand failure mechanism and the influence of environmental factor such as rainfall, earthquake, and etc. Now, 5 is to enable the redesign of failed slope. If we have, for example, our design, our construction of the slope fail, it is very common that we would like to strengthen the slope or to provide some remedial measures where necessary. And number 6 is to study the effect of seismic load on slope and embankment. So when we design and construct slope under the static condition, under the its own weight, for example, where we need to design that slope due to earthquake also. So usually if we have a slope, for example, like a dam, this is a man-made embankment, we call. We have several geotechnical concern. Number 1 is ground bearing capacity. Number 2 is the ground settlement. If we have relatively soft subsurface condition, and then we need to worry about what is the settlement. And the third one is the seepage analysis, how the groundwater flow through our embankment. And the fourth one is this one, is the slope stability. So we need to calculate the stability of the slope, and we need to design so that this dam is stable during the operation of the dam. Well, let's see the factors contributing to slope failures. Here we have, there's a table 1.4 and 1.5 here. And on the left is a factor that cause increase in shear stress of the slope. So if we have a slope, there are two components that we need to consider. The first one is the shear stress in the slope. So that is mobilized, what we call is mobilized stress. So that is because of the, let's say, its own weight, for example, because of the loading due to the rainfall, loading due to the dynamic load, whatever that generates stress within the slope, that we call the mobilized stress. Okay. For example, here we have a slope. If this slope tend to fail, and then this slope generate what we call a shear stress in the failure, its failure plane here. So this is a shear stress. So this shear stress could be generated by many of these possibility. Okay. And the second one is actually the strength of this soil. So in this soil we have a shear strength. So there is a strength of this soil. We call it tau strength. Okay, tau S, and this is tau depel. So tau D is the developed stress, and tau S is the shear strength. So basically, in slope stability, we make a ratio of shear strength and developed stress. Okay. Okay. This is a list of the shear stress that could be subjected by the slope itself. For example, due to erosion by stream and rivers, by glacier. Okay, there's a lot of factors here. For natural slope, for example, fall, slide, settlement, human activity because of we cut, because of excavation, removal of retaining walls, and maybe also because of the drawdown of the water reservoir in the dam. So many factors that could cause the increase of stress in this slope. And also transitory effect because of the earthquake. The slope is under static condition is stable, but under earthquake the shear stress increase. So this will increase, causing this what we call safety factor will decrease. If this safety factor less than 1, and then we call the slope is unstable. So it's pretty much depend on the strength of the soil. So if you have a certain type of soil, that soil has a specific strength. Okay. Okay, this is another one you can see later on. Okay, how about the strength here? factor that cause reduce. So this safety factor could be less than 1 due to the shear strength decrease, right? Or the developed stress increase. So that would make the this FS, the safety factor, going down. And if it's lower than 1, then we call the slope fail. Okay. So here we have several factors that causing the reduction in shear strength of the slope because of the composition of the soil, structure of the soil, secondary or inherited structure, stratification, and then wetting and drying process due to precipitation, hydration, okay, removal of cemented agent, effect of pore pressure. Usually, if we have saturated soil under a certain loading, for example, due to shaking of an earthquake, for example, the shear strength of the soil will reduce because the increase of pore water pressure. Okay. Also, change in structure, stress release, and also structural degradation of the soil itself. So, soil actually has a very complicated nature, like a very complicated behavior, because of many factors. The strength of the soil could reduce. Okay. Okay, let us move to factor of safety and Mohr-Coulomb failure criteria. I just start introducing the safety factor, but later I will explain it in more detail. Let us now define the failure criteria of the soil and rock. Okay. We have a failure criteria called the Mohr-Coulomb failure criteria. Actually, this failure criteria is based on the formulation by Professor Mohr in 1900. He found that the normal stress and shear stress has this kind of relationship. So if we have, this is a Mohr circle for you from civil engineering or from rock mechanic. So we call sigma 3 and sigma 1. For other sigma 3, we have another Mohr circle for more higher sigma 3, and then we have another circle. Well, according to Mohr, this Mohr circle is tangent to each other as pressure on the sigma 3 increases. So this is actually showing the dependency of the shear strength of the soil with the confining pressure. The higher the confining pressure, the higher the strength. And the failure envelope is actually not linear, but rather it is tangent to the Mohr circle. Okay. So that is Mohr. And the second one is Coulomb. You know the Coulomb friction rate, Coulomb friction. This is actually the same Coulomb that formulate the friction between material between two different type of material. He suggests that the shear strength of the material is formulated showing the cohesion and also the friction angle phi. So we have two parameters to define the shear strength of soil or rock. One is what we call stress independent parameters. C, this is stress independent, and the second one is phi. So friction angle. This is a stress dependent parameter. So we have C and phi. But Mohr so that this is actually not linear. But later on, Coulomb and Mohr formulate this is these two professors live in different year, different generation, but later on Mohr and Coulomb formulate, or Coulomb just call this formulation as Mohr-Coulomb failure criteria. With the this envelope is not non-linear, but just simply linear in nature. Okay, so this is the formulation. Then we just very simply with these two type or two parameters we can calculate, or we can formulate the shear strength of soil. This C and phi can be obtained from laboratory, and then we test in the laboratory by conducting several triaxial tests, for example, like this, and then see the envelope of that circle, and then we'll find the parameters C and phi of that soil. So this is very important parameter, what we call stress independent parameters C and the stress dependent parameter phi. As mechanically, or by state of stress, here we have three state of stress. One is point A here. Point A is within the envelope of the Mohr-Coulomb. So if the state of stress fall below the envelope of the Mohr-Coulomb, we call that soil is stable. Okay, so point A is stable here. For example, here in this plane, here's point is AB here, plane AB. So there's a combination of the sigma. Sigma is normal stress, tau is shear stress. So that combination will determine whether a soil is stable or not. So point A is stable. Point B is just fail just because it's within the envelope. And point C here is impossible because it's beyond the envelope. So that is not point C cannot exist here. But point B is under unstable condition. Point A is under stable condition. Okay, the safety factor, as I already tau F we call it average shear strength of the soil. Usually also we call it tau S, is the same thing. And divided by the denominator here is the tau D. Tau D is the developed stress along the failure surface. So basically we evaluate the the safety factor of the slope by comparing these two shear stress within the slope failure surface. As we can see here, for example, this is failure surface, and then this is tau D, for example, and the shear strength here is tau F, and then we compare the tau F and tau D. Later on, we will go in more detail on how do we calculate or how do we analyze this safety factor. Okay, we will formulate the shear strength as this, as you already know just now. Okay, now how do we formulate a safety factor? The shear strength is easily formulated or easily calculated as long as we know the coefficient, the parameters of the soil, which is in this case is C prime, and phi prime, and also the normal stress within the planes. As long as we know the normal stress within the plane, and then the shear strength of the soil can be calculated very easily. There is a C prime here. There's a C. C prime is, we call it effective parameters. Why we call it effective? Because in soil, not like in rock is very massive, right? But in soil, we have water. We have water within the pore of the soil. So in this case, we have a pore pressure. So we define effective stress as total stress minus the pore water pressure. So because our reference is effective stress, so this is effective stress, and this is total stress. But within the soil, we have pore water pressure. Okay, so our reference is usually effective stress. When we test our soil with the reference to effective stress, then the parameter that come out from the test, we call it effective parameters. So we have C prime and phi prime. Okay, so that's for reference. For you who are from the civil engineering measure, you will understand these parameters. Okay, now we will formulate the safety factor as the okay. Here again we have shear strength. Okay, tau F, shear strength, and the developed stress. So the shear strength is formulated as this, but the developed stress we will call it is formulated as a similar formulation as the shear strength, but here we have C sub D and phi sub D. So this is actually developed cohesion and developed friction angle to make it equivalent to the formulation is equivalent to the shear strength, but actually this is like imaginary cohesion and imaginary friction angle, so that we can formulate the developed stress within the in the same way, the same manner as the shear strength. Okay, and then we have what we call FC prime. So this is a safety factor with the reference to cohesion. The formulation is the definition is C prime divided by C sub D prime, and we have another safety factor, what we call F phi prime is equal to tangent of phi prime divided by tangent of phi developed prime. Okay, so this is actually just a way as a medium to formulate the safety factor, and when we can make the FC prime equal to F phi prime, then we can define the safety factor. This will take some kind of effort to find out how we can make the FC prime the same as F phi prime through a little bit trial and error and satisfy the formulation of this equation. Okay. Okay. This as we already understand what is the safety factor. In this case, safety factor higher than 1 is we call the slope is stable. But when safety factor is less than 1, and we say the slope is unstable or fail. Okay, when we design a slope or when we evaluate a slope, we need to make sure that the safety factor is higher than 1. But there is a criteria to evaluate that the slope is stable under different conditions. Here is recommended minimum values of safety factor for slope stability, particularly for a man-made slope. Even though for natural slope, we could evaluate the stability of slope through the formulation that we have discussed briefly. And when the value of the safety factor out of the calculation show a number or value lower than this value that's shown in the table, then we can say that the slope is unsafe. Okay, so let us start with the recommended minimum value of safety factor for let's say if we design a slope for man-made slope, then slope with the cost and consequences of failure, let's say cost of repair comparable to cost of construction, then or no danger to human life or other property of the slope fails when it fails, if the slope fails. Here we have two conditions also, uncertainties of the strength measurement, is one is small, one is large, and then we define the value is different. So 1.25 because uncertainty is small, so that means we are very more certain, we are more confident with the variation in the strength of the soil, and then we need a lower number, so it is 1.25. If it's the uncertainty is larger, then the value is 1.5. Construction or equal danger to human life or other valuable properties if slope fails. You can see if there or is open pit mine, for example. That is something you consider risky, for example, and then you could well, it depends. It is temporary or it is permanent also, and this is the value that recommended for design. Okay, let's move to analysis of slope stability. I'll just explain briefly because the time constraint here in this course, because it's only 2-hour course. It's impossible to cover all of the methods of calculating slope stability analysis. So I will just the method of slope stability analysis for infinite slope, which is basically, and then the second one is for finite slope for also simple soil layers. Okay. There is a reference for you who would like to know more about to study more about slope stability analysis. You could refer to some of the references on slope stability that you can find, or you can take other more advanced lectures on slope stability. Basically, this course is just to provide basic knowledge, introduction to slope stability, how it is calculated in general, and what is available method of evaluating the slope. Okay, we start with the infinite slope. Infinite slope means if we have the thickness of the slope, in this case is h, is the same all the way across this slope. So this means the height of the slope is very small compared to the length of the, for example, this is a very hard layer, for example. So the slope will just fail incorporating the whole mass of this layer. So, okay, so this means the x compared to the length of the slope is very small. So that we can consider as an infinite slope. The other category of the slope is finite slope. Finite slope, for example, is let me just go to the finite slope just for comparison, so that you can compare. This one, for example, this is a finite slope. You cannot. We have several layers, and also we have a more complex geometry, so that the slope cannot be same thickness all the way through the slope. So this one we call it finite slope. For example, like this, the slope failure is in this plane. Okay, so it's very different from what we just this one infinite slope is just a layer of one layer of soil that the plane itself is within the slope of higher strength. Okay, this is infinite slope. So we can represent this slope failure as a free body. Yes, a free body. This one just a block of of material here. We'll call it the free body with the length of L and with the height of H. Okay. We can see what is the forces acting on this failure plane. So this is the failure plane of the slope. So if you have the weight of this area, this the weight with the area of the body multiplied by the unit weight of this soil or rock. Okay, we call it W. So that is the weight. So this weight is actually will act on the plane, and if we have weight, and if we distribute the weight uniformly through this plane, divided by the area of the plane, and then we have a normal stress to that plane. So we have normal stress to that plane. What you can see is you can just simply find out what is the shear stress or develop to this plane. So that is the what we call induced stress or developed stress. Okay. Okay, let's see more clearly here. This is W. This is still forces. We can break down or make the this W to this plane and normal to that plane as NA and TA, or TA and NA here. Okay, and this is the reaction and R, and then this TR is also the reaction of this TA. So if we have W, we have R as the reaction. So basically we have equilibrium between the internal forces due to the weight of the slope and the later on we can evaluate the strength, the shear strength of that plane within the soil due to the NA normal to the plane. So if we have NA, we can calculate the normal stress in that plane. So we can formulate that. You can go along with this mechanics or with this geometry, so that we can calculate the normal stress and the shear stress within that plane. Okay. So we have developed stress here, just transferring from forces to normal and shear stress through the area of the base. Okay. Again, finally, we just use this formulation of safety factor as C prime sigma tan phi divided by C sub D plus sigma tan phi sub developed stress. The formula that we already discussed earlier. And then by calculating the each component of the safety factor, FC prime and FV prime, basically we can formulate the safety factor. Finally, ultimately, this is the formula for calculating the safety factor for infinite slope like this. Okay? if we have this soil has a C prime and V prime as a parameter, and so simply I just put it in an Excel very easily. You can find you can calculate the safety factor of this slope, this infinite slope. Okay. If you have granular material mean when the cohesion is 0, so that means you only have the friction angle of the material. For example, sand layer, sand soil layer. The safety factor is just simply tan phi tan divided by tan beta, where beta is actually the slope. You can find this the usefulness of this formula in waste dam, for example, for the one who from mining major here, or from the rock mechanic for mining activities, waste dam. So if you just pour the material, the waste dam, as in an angle of repose, you just dump it from a truck or from container, you will find the slope just forming. You just pour the material. Okay, you just find the slope of that material dumping is what we call angle of repose. Yeah, angle of repose. This angle of repose is actually the because and when you dump the material, the safety factor is actually equal to 1. So that means the beta, the slope angle, is the same as the friction angle. Okay, so in this case, phi is equal to beta for direct dumping of material. So in mining, usually for rock dumping, maybe the phi is equal to about 38 degrees, something between that, 38, 37, something like that. Okay, so that is the safety factor of the slope. Other complication of the slope could be when we have groundwater flow through our slope. Sorry. When we have groundwater flow through the infinite slope, so we need to consider what is the pore water pressure that occur in this failure plane. So the pore water pressure here is depending on the seepage. We can use what we call equipotential line and flow line. So usually we have a flow line like this. We have an equipotential line like this. So you draw a flow net within the slope, and when you can draw the flow net, and then finally you will be able to estimate what is the pressure head within this in this plane. With the pressure head, later on you can multiply it by the unit weight of water to find out the what is the pore water pressure here. So when we have the pore water pressure, you can calculate the effective stress as the total stress minus by the pore water pressure that you calculate from the flow direction. So with that, you can also modify revise the safety factor formulation based on the groundwater flow. So we have that formulation. I think you can just follow these notes. I just take these notes from a textbook that we use. Okay, this is the result of our safety factor formulation. when we have groundwater flow through the infinite slope. Okay, let's continue with the finite slope now. Finite slope is a slope that has where the slope or the slope failure plane is not infinite. For example, like this is finite. Okay. So the is not as is far from the infinite slope. So in this case, we can also make equilibrium of forces within this plane. When we have a very uniform soil like this, or uniform rock, for example, we can define a plane, failure plane. We assume that within the zone, and this is its failure plane, and then after that we calculate what is the weight, similar to what we have done with the free body of the infinite slope. So with that, with similar calculation of the slope, then we again define or calculate the safety factor based on this shear strength of the soil in this plane. That rock, and then we can what is the developed stress within this plane as well. Can formulate the geometrically and satisfy the Mohr-Coulomb failure criteria as long as we have the cohesion and the friction angle of the soil, of the material itself. We'll be able to calculate the difficulty here is actually in any plane like this. So the slope could fail in different plane, but we don't know what is the critical planes to make the safety factor the lowest. So basically, in this kind of slope, we will find the what is the angle of the critical slope here by just finding the extreme value of the cohesion, so that the least safety factor is occur within that plane. So here we calculate the tau to make the extreme value of this. So you just differentiate the CD as formulated here to by the theta, and make that derivation equal to 0. And then with that, you, as long as you already find the theta out of that, then we come back with the formulation to find out what is the safety vector is. Okay, here is a formulation of what is the critical height of this slope to make the safety factor equal to 1. So usually in practice, we would like to know what is the critical height of a slope when we set the safety factor equal to 1, knowing the parameters of that slope. Okay, so this is a linear failure. In many cases, here is not a plane, but rather it is a circle. Most of the, as long as we have in soil particularly, we have the failure failure of the soil as a cyclical failure mechanism. So this is called a toss circle, and this is called a slope circle, for example, like that. And this is we call it a base failure circle. So actually the circle go beyond the slope, this level, but go to the depth of the higher strength of soil. For example, here is a rock or lens layer, for example, and then the slope failure will go above that higher strength layer. So we have many many possible failure mechanism according to, depending on the different type, according to the steepness of the slope, depending on the shear strength of the slope, and also depending on the whether we have other soil layers beneath. Here we have example of a method of slices. So as we summarize here, we have a finite slope that could be either plane in nature or could be circle in nature. And if we have different layer of soil, for example, like this, then the mesh procedure or the circular procedure cannot be used as a method of calculating safety factor. Rather, we use what we call method of slices. So if we have, for example, this one, we have a failure plane here, if we assume like that, and then we have a different layer. For example, this is layer 1, layer 2. You cannot apply mesh procedure method, but rather you need to use a method of slice. And then because why method of slice? Because each slice here has different characteristic. So example, layer 1, for example, this is 1, 2, 3, and so forth, or A, B, C, D, E, F, for example, like that. So slice A, B, C, D, E, and F has different characteristic because it consists of different layer of soils, different shear strength at the base of this slice. So each slice has different characters, so that each slice need to be evaluated. Not like the mesh procedure, you can just use the whole mesh as a one. So this is actually much simpler compared to the method of slices. When you use method of slices, you need the help of computer calculation. You need for calculating the slope stability, its safety factor for that. Okay, mesh procedure, I will go very quick on this. For you who interested in more detail on how to calculate the mesh procedure slope in homogeneous clay soil, you can refer to the reference that I put in the in this document. Okay, PowerPoint. I don't have time to explain in detail each of this method, but basically the mesh procedure is applicable to homogeneous soil, whether it's clay or whether it is sand soil or granular soil. In geotechnical engineering, in soil mechanics, we differentiate between sand or granular soil, the soil. Okay, basically, what is the mesh procedure? Procedure is to assume the whole mesh of this as as one mesh. And the calculation of the forces is by just this or considering the whole what is the what is the hello, can you hear me now?
Yes, yes, clearly, Pak.
Okay, okay, let me
Yes.
continue again.
Yes, please.
Here. Okay, can you see the screen?
Yes, now.
Okay. The connection is bad, so I just keep talking without anybody listening. Okay. The value that we can use for calculating the effective factor of the slope. Okay. There's a procedure. There's a graphic for helping the calculation of the slope. Okay, I just go on. Hello.
Yes, Pak.
Okay. Bisa lihat lagi sekarang? Halo. Can you hear me now?
Yes. Yes.
Hello.
Yes.
Yes, I can hear your voice.
Okay. Okay. Let's start again.
Yes, please. I think the internet connection is bad.
Okay. Oh. Can you see now? Hello.
Yes, I can.
Yes. Okay. There are several charts that we can use for the slope stability analysis through mesh procedure analysis. I just go through this ordinary the method of slices. The third one. The third one is the method of slices by the method what we call ordinary method of slices. So the slope is divided into many slices like this, 1, 2, 3, and so forth. And then each of the slices the internal forces for each slices is elaborated, and then we calculate we analyze the safety factor of all of the slices through Okay, this is a method of slices of calculating the safety factor. Actually, we have different methods, so many different method of slices. One is ordinary method of slices. The one is Bishop simplified, Jumbo simplified, Corp engineer, and so forth here. And each of this method is actually satisfying one, two, or three limit equilibrium. For example, ordinary method of slices satisfy only one equilibrium, which is in this case moment equilibrium. So, so the X force equilibrium is not satisfied. The second one is not satisfied. The in Y direction is not satisfied. So only one moment equilibrium is satisfied. So that is for ordinary method of slices. So we have other different type of method of slices where two or even three, all of the equilibrium requirement is satisfied. So the more equilibrium is satisfied, the better the method. So for example, here, this is considered good, you know, because it's yes, yes, yes. But when it's only one, this is not good. That is the concept. But here we have two yes, yeah, two yes. This is very good, and this is good. Okay, like that. Okay. The second one is the Bishop method because there are two equilibrium is satisfied. This is more complex. The calculation or the static equilibrium that need to be satisfied become more complicated because each of this section, these slices need to be to satisfy the equilibrium. Then you need to have you can actually use an Excel for this, but somehow the calculation is more complicated compared to the previous one, compared to the ordinary method of slices. But basically, with the help of computer calculation, so all of this equilibrium for each slices could be fairly easily in computer. Okay? So a lot of force equilibrium in this each of these slices. So basically, later on you can just formulate the safety factor based on the each of the slices integration, so that finally you can calculate the safety factor of layered soil. Okay, some of the slope. Okay, I just complete the calculation of. Let's go a little bit. For example, we have an embankment here. And then at the bottom we have, for example, clay soil. This clay soil is relatively not put load on top saturated. For example, you have a dam, for example, or you have a tailing dam, reclamation project, etc. In relatively soft soil, for example, this type of behavior during construction. This is during construction. This is the safety factor. During construction, the safety factor is getting lower. But when the embankment is already there, when the project is already, construction is already completed, there is consolidation of the soil that make the safety factor increase with respect to time. So as the time goes, the safety factor increases. Okay, so this is shown by this curve. The cause of the loading is increased, and then after the construction, the load is constant, but somehow the excess per water pressure decrease because of excess per water pressure, the shear strength increase. So the opposite is true when we have excavation. So, for example, we make a reservoir for the oil drilling. For example, for the oil company, we need to construct we have construct the reservoir, and then you excavate the existing soil. So what could happen is if we have a clay soil, for example, here, then the safety factor will reduce with respect to time. Okay, so that's some behavior of clay soil with respect to stability during operation of the facility, dam or reservoir, whatever you construct. Okay, this is just a brief introduction, brief highlight on how the slope could reduce in safety due to earthquake loading. So basically, if we have a dam or we have whatever slope, existing slope, under static loading will be very stable. But be careful then when you have an earthquake, so the earthquake will transmitted to the site, and there is some modification of the site, whatever the site your dam. Example, you have for beneath the maybe soft soil or hard soil, whatever. There is a earthquake will the dam, the embankment that could decrease the safety factor of your slope. This is an example of Indonesian acceleration that you will use for calculating the safety factor of your slope. This is an example of how the safety factor will reduce with the increase of the seismic coefficient. So that, and then when the safety factor is equal to 1, then we say the slope is under critical condition. When the seismic coefficient getting higher, your slope will fail. And that is illustration on how the slope or the dam or the slope will
To our participant, I think the internet connection of Bapak Professor Wayan Sengara is not stable. So we will wait until he join again.
Hello?
Sorry, can you hear me?
Yeah, is it okay now?
Okay, yes. You can continue, please.
Of several example of cases in slope stability analysis. We have a dam here. We have estuarine dam with a reservoir close to the sea. And we have several soil layers and showing the application of a method of slices. We have a Bishop method, we have Janbu, Morgenstern price to show what is the safety factor of each of the method in this case. And also here we have slope stability showing the value of the safety factor for other slope. In this case, we have several potential failure, but the critical failure is in this zone. Previously, we have potential safety failure plane is deeper. So in this this is the most critical, the lowest critical safety factor, which is 1 point showing here. This is slope stability analysis using finite element program by IVC action. Later, Priyadi, don't miss this lecture. I think there's going to be a lecture on the finite element method to calculate the safety factor for slope stability. And this is the example of slope stability adapting finite element method. In this case, okay, this is a potential failure with a safety factor of 1.4. In other case, through seismic loading due to earthquake, we have this potential failure with safety factor of 1.2. This is the actual condition of that slope. Here's another example of applying a finite element method for open pit mining. So we have a different type of rock formation in this case. As you can see, some might be reinforcement here. So this is an example of southern slope of Jiangmen copper mine in China. Another one here is also open pit mine using different limit equilibrium method, similar to what I just showed previously, and also comparing with finite element method as well, showing different value of safety factor from different failure plane. So actually we can compare the limit equilibrium method as what we explain, elaborate in this course this evening, and also with element method. This is subjected to earthquake load of 0.3 G and see what gonna happen. So in this case, you can see the slope will fail under the earthquake load of 0.3 G, even though the slope is stable under static condition. If an earthquake of 0.0 G occurs, so we can make a prediction out of this analysis. Sorry again for bad connection. Case example that I would like to share with this is all that I would like to present this evening. So this is the end of the lecture. So the end of my presentation. This is the end of the lecture. So later on we can have we can.
Sorry, Prof. Wayan, I can hear your voice. Prof. Wayan, can you hear my
Hello?
voice? Yes.
Yeah, we can continue with question and answer now. So that's the end of my presentation, the end of the lecture.
Okay, thank you. Thank you very much, Bapak Professor Wayan Sengara, for very interesting presentation about slope stability. And now we are going to the question and answer session. You can see in the chat box, there are several questions from participants. You can read this question. The first from Mbak Rifa. Can you see the question, Professor? In the chat box. The first question from Mbak Rifa. What is the main characteristic of failure that caused by earthquake? And the next question is, do you have experiences in using multi-channel analysis of surface wave or spectral analysis of surface wave method to check the soil stability? How this method works? You can answer directly.
Okay, can you hear me clearly? Hello?
Yes, yes.
Okay, thank you. Sorry about the bad connection. I'm not sure
No
why.
problem, sir.
Okay, the first question is related to what is the characteristic of the failure due to earthquake. Well, there are many characteristics of failure due to earthquake. Basically, if we don't have, or for example, if you have typical soil layers that not consist of sand or saturated sand, then you have similar characteristic of failure due to static loading, except that you have now earthquake loading, and then we can calculate the or evaluate the safety factor, and as long as the safety factor less than 1, and then the slope is just fail, similar to let's say slope failure under static loading, under its own weight. But if you have a slope above saturated sand, for example, like what we see in one of the illustration or one of the picture at the early of my lecture slide showing the failure of a dam, there was a liquefaction occur at that dam. So that is due to earthquake. Liquefaction is a state of the sand from solid state to become a liquid state. So you can imagine how the solid state of sand after the shaking due to earthquake, then the soil become like liquid. So this is very popular mechanism or characteristic of a slope that fail under earthquake loading. Okay, the second question is I'm not mistaken, I can mention about multi-channel analysis of surface wave. This survey, this geotechnical subsurface survey that is conducted using this method is very useful in the shear wave velocity or the compressive wave velocity, that we can identify different layers of the soil. So that in that case, as long as or in condition that we have a limited number of boreholes in our project, then the multi-channel analysis of surface waves could be very helpful in providing the soil profile that is very is needed in providing the model. In building a model of slope stability. So we have more data, we have more, so the uncertainty of the site is added, I mean is limited, we have more confidence in our site profiling, so that also we will be more confident in this and slope stability safety factor that we calculate from our analysis. I hope that will answer your question.
Okay, thank you for the answer. And the next question from Bapak Hendro Atmojo. Can you see the question? From Wayan.
Which one?
There are two questions.
Could you read the question?
Okay.
Armita, could you help read the question? Somehow I can find.
From Pak Hendro Atmojo, the first question: what is the simple method to slope stability analyze? And the next question is: what is the various methods to improve stability of slope? Okay.
Okay. Thank you, Pak Hendro. How are you doing? I know Pak Hendro very well. He's my friend. What is the simple method of calculating or analyzing slope stability? In the presentation, I present the three types of methods. One is very simple one by just using calculator, by using your handphone, your calculator and your handphone, you can just find very easily calculate the safety factor of the slope. It is in the case of infinite slope. If you identify your slope is infinite, and then you just need what is the C or phi of the soil parameter, and then with the simple formula you can calculate the slope stability safety factor. But in more complex situation condition where you have different type of layers of the soil, then you can use Bishop method, and which is now all is computerized, like in the slope W method. Many software is now available to calculate the safety factor as long as you can provide your soil profile and parameters, and then it's very easy for you to well, the other method is using finite element. This topic will be explained, will be specifically explained through 2-hour lecture also next week, right, Pak Wahyudi? It's next week, right? So that will be very interesting. So don't miss that lecture. Even though for illustration, I saw some of the example of slope stability calculation using finite element method. For soil reinforcement, for the slope reinforcement, currently, well, if you have a slope which we consider unsafe, for example, let's say the safety factor is less than a certain value, below the required minimum safety factor, you can reinforce or you can improve the slope by many methods, such as soil nailing, such as providing fabrics to the slope, reinforced through sit or bore pile, soldier pile, and so forth. So many methods apply, or we can exercise in the modeling so that we can come up with very optimal reinforcement, so that we make sure that the stability of the slope is maintained both under static condition, under rainfall condition, and also under extreme condition like earthquake, for example. I hope that answered the question.
Okay, thank you, Prof. Wayan, for the answer. You have another question from Pak Untung Riyadi. The question is, what finite slope analysis can deal with heterogeneous soil profiles, anisotropic strength characteristic, fissured soils discontinuities, complicated boundary condition, and complex loading in both 2 and 3 dimensions? If yes, how? If not, what method to solve it? You can answer that.
Hello.
Yes.
Can you hear my voice? Okay,
yes.
that's difficult
Clearly,
one. This is a difficult question. Well, in practice, we may experience difficult or complex condition like what you asked. In that kind of situation, for example, our soil layers or rock layers consist of jointed rock, for example, very difficult condition. There is a soil or maybe groundwater flow through the slope, or even finally there is a potential earthquake to the slope. There are 2 main thing that we need to consider. One is the characterization of the site. You need to have a very good characterization of the site, including the subsurface layers. If it is rock, and then you need to identify the jointed. You need to make what we call a rock mesh rating of the rock. You need to have you need to identify the characteristic of the rock, RQD, modulus, rock mesh rating, and so forth. So, but basically, with all of the complexity, you just recommend the rock parameters out of that based on the simple Mohr-Coulomb failure criteria. And then if you have a 3-dimensional nature of your slope, and then you don't have any choice other than using the help of a three-dimensional software, such as finite element program or finite difference program that accommodate three-dimensional geometry. So that is very common at this time. I have an experience of conducting three-dimensional slope stability analysis of waste dam here in Indonesia, in Freeport, where we have some mix of waste dam and also the original rock. So that's something that we could do. Okay, I hope that answers your question.
Okay, there are question again in the chat box from Ayu Prativi. The question is, as on your slide, we need to know the soil parameters such as bulk unit weight, cohesion, and friction angle of soil that to analyze the slope stability. If we use geoelectrical method to investigate the soil stratigraphy, could we know this kind of soil parameter?
This is an interesting question actually, the slope stability is a quantification of soil parameters and mechanic equilibrium or limiting shear strength of the soil layers, the subsurface layer, and the induced stress. In geotechnical engineering, we need this quantitative parameter called the soil parameters such as cohesion, friction angle, and other parameters that we usually adopt in soil mechanics or in rock mechanics. Right? Well, that will need an effort to identify or to make a soil field or laboratory test to obtain these parameters. The use of geoelectric method to investigate the soil stratigraphy is useful, but somehow you cannot get the specific cohesion and friction angle out of this geoelectric method. Some of the result through empirical correlation could be made, but limited to modulus usually. From geoelectric method, you can correlate to shear modulus or to Young's modulus, but somehow it is not easy to correlate through to the shear strength, like C and phi. So make sure that for specific slope, you do both. You do geoelectric method, but we also do some drilling through soil sampling and do laboratory testing.
Okay, thank you for the answer. And the next question comes from Wisandi. Thank you, Mr. Wayan, for the explaining. I have a question. According your explanation, there is Fs number less than 1. That means failure. There is method to increase Fs number?
Yes. Of course, we have a method of increasing the slope. I think I just also answer a question related to this just now. I hope that you also listen to the answer with the previous question, that we can increase the safety factor of the slope through various methods of soil improvement, reinforcement, nailing, for example, through bore pile, through or a reslope of the slope and provide some buttress. So many methods in geotechnical engineering that we can propose to increase the safety factor to be higher than 1 according to the guideline, according to the specification. For example, like in open pit mine, usually the safety factor is the requirement is 1.2, so say. But if you find the safety factor is less than 1.2, and then you need to reslope it, or you need to lower down the groundwater, for example. So that is some example of increasing the safety factor through the decreasing the pore water pressure within the slope. If you cannot do that, you need to re-slope to make the slope more gentle. So I think depend on the practical case by case situation. So that is actually the challenge on how we stabilize our slope in different types of situation or projects.
Okay, thank you for the answer. You have another question from Bariska. Thank you for sharing, Professor Wayan. I would like to ask you first, can a finite slope analysis be carried out for the groundwater case as well as for the infinite slope?
Say again. Sorry, I cannot.
Okay.
Which one is that question?
From Bariska, there are 3 questions. Can a finite slope analysis be carried out for the groundwater case as well as for the infinite slope?
Oh, yes, of course. You can do the with relatively easily to calculate the safety factor of infinite slope with or without groundwater condition, without seepage or with seepage. So you can find out in this PowerPoint later on. There is a different formula that you can apply for calculating the infinite slope under both with or without groundwater flow. I'm not sure hopefully that answers your question. So you said there are 3 questions. What is the other 2 questions?
Yes, the next question is, what are the advantages of finite element modeling compared to other numerical models in modeling slope stability?
Oh yeah. Well, the advantage of using finite element method is you have you can accommodate more complex geometry, more complex soil layers within the slope. So if you use a more simpler method, then many of the variable is limited to be applied. So for complex geometry or complex situation consisting of soil layers, groundwater flow, and so forth, or even with some slope that require deformation. For example, you want to know what is the deformation of your slope, then the use of finite element method is more appropriate. But for simpler problem, you can just use limit equilibrium methods, such as applying Bishop method, for example, applying Janbu method, as what we already discussed in this course. So with relatively simpler calculation with the software also, because there is a software that can be used for that very quickly, with much simpler approach, with much simpler method, you can get the same result. similar result.
Okay, the last question, Professor. Have you ever calculated slope stability from geoelectric or electromagnetic data? Can you explain the data required to relate it to slope stability? Sorry, Prof. Wayan. Can you hear me?
Could you say again? I missed the last question.
Okay. The question is, have you ever calculated slope stability from geoelectric or electromagnetic data? Can you explain the data required to relate it to slope stability?
Mm-hmm.
Yes, that's the question.
Not particularly have an experience directly using the geoelectric method to correlate with the geotechnical parameters, but limited to the soil profile, the depth of the or the type or the depth of the soil layers. Mostly we use refraction survey or multi-channel analysis of surface weight to identify the soil layers and then correlate this shear wave velocity to the modulus that is applicable to finite element calculation for stiffness of the material of the soil layers.
Okay, I think this is the last question. So I think now we are going to the next session, the photo session. Pak Wahyudi, do you have? Okay.
Okay, yeah.
So thank you so much, Professor Wayan Sengara, for very interesting and useful presentation about slope stability analysis, theory and practical, especially in geotechnical engineering. So everyone, we are going to the photo session. So please turn on your camera. There are so many questions from the participant, Prof. Wayan. Mbak Rifa, can you help me to capture the slide?
Yes, of course, Mamita.
Yes, I will prepare the slide and send it to you so that later on we can distribute it to all the participants.
Okay, thank you. Thank you very much.
Okay, now is photo session. Please open your camera and keep your smile so your face is nice on a screen. Now is first screen, okay, first slide. 1, 2, 3. And then a second slide. 1, 2, 3. Then third slide. 1, 2, 3. Okay, keep your smile. And then the last page or the last slide. 1, 2, 3. Enough, Mbak Mita.
Okay, thank you, Mbak Rifa. Thank you very much, Prof. Wayan, for your sharing this night. Pak Wahyudi, do you have something to say?
Yes, on behalf of the Department of Geophysical Engineering, we thank you very much to Professor Wayan for your interesting lecture, and thank you for all participants. And we will meet again tomorrow yeah, at 13 o'clock. So yeah, so I think the session can be closed. Okay, again, thank you very much for all, and yeah, goodbye. So
Okay, so tomorrow the session is with Prof. Tadanori Goto from University of Hyogo, Japan, and Dr. Sina Sanian from University of Oklahoma. See you tomorrow, everyone. Thank you very much for joining us. Thank you, Prof. Wayan, for joining and share your knowledge. See you tomorrow. I end the session.